Okay, this segment is going to cover soldering in vapor phase, touch on the process and rudimentary machine design. This is the basic outline for every machine, be it standalone or inline. Even the inline systems are actually staged in that the front load, the buffer section on the front side, which convey boards into an elevator. The elevator would move vertically in and out of the process, and then you would have an offload buffer that would take the boards from the elevator station out to the next operations. So this is the process chamber. You have a tank acting as a reservoir with liquid medium. You have heating elements. In the Ascon systems, these are clamped to the outside of the machine, which makes maintenance and heater replacement in the event of a heater failure much easier. The tank is a single unit, so there are no seals to fail around the tank, which makes maintenance, as I say, that much easier, cleaning a lot easier. So once you apply energy to the heaters transfer energy into the liquid medium. Liquid medium creates your vapor blanket. Circuit board is lowered into your vapor blanket where the thermal process obviously occurs. Then we have cooling coils on the top side of the machine which convey cold energy to the circuit board for the cooling process, and they act as a means of further condensation for vapor in order to mitigate any vapor loss from the system. So in terms of how the process is working, you have a circuit board. That circuit board is cooler when it enters the vapor than the vapor itself. That creates an immediate liquid film around the circuit board, and that liquid film is your oxygen barrier. Your vapor blanket is then feeding that liquid film using vapor molecules to transfer energy through the liquid film into the circuit board. So in terms of energy efficiency, and this is really where the vapor phase process secondary benefits occur in regards to the cost of ownership, 100 watt energy generation on the outside of the system as heat is conveyed as 100 watts of energy generating vapor, and that vapor carrying 100 watts of energy conveyed through the liquid film into the circuit board. It would be a stretch to say that this is a lossless system, but it is, in terms of energy efficiency, far superior to a convected system using air or nitrogen. Additive benefits in terms of the use of a vapor through a liquid blanket. The top image here illustrates once you have your liquid film encapsulating the circuit board, that liquid film is actually going to capillary in and around the I/O of array devices. And so consequentially, as your vapor molecules continue to feed the liquid film around the circuit board, you're conveying energy to that liquid film, and that energy is being conveyed in to each and every I/O. It is physically impossible to have a temperature delta through this liquid film from the exterior I/O to the interior I/O. So you are guaranteed thermal stability of the process that's occurring around the joints from the outer to the innermost points of connection on the circuit board. Compare that to a convection process. You are in essence utilizing conduction of the energy through the device itself or into the circuit board, and then from the circuit board back up and into the I/O. And consequentially, you are very, very likely, and obviously we've all seen this, going to see differences in joint structure, joint quality, and joint integrity from the outer I/O to the inner I/O. So when you look at the coefficients of thermal transmission, very, very simply, if you were to look at reflow soldering with convection, you have measurements of between 40 to 120 watts. Compared to vapor phase, you are up in the 500 to 700 watts. So in essence, you're looking at factors of 10 times greater conduction per unit of energy used in the system. That gives you far greater control of the process itself, and obviously it leads to much greater efficiency in terms of cost of operation. So looking at profiles of vapor phase versus convection, and talking to the periods associated to thermal saturation, obviously a convection profile, as we understand them, all encompass this plateau for various reasons, be it for stated flux chemistry activation, or be it for stabilization of components which are varying in mass and obviously reacting differently in terms of their ramp rates. And then here in the yellow we have a very linear profile which illustrates a typical vapor phase profile. And the two things to take from this slide are, one, peak temperature, recognizing that your peak temperature in vapor phase is controlled by the fluid boiling point. And so consequentially we are able to hold peak temperatures at a constant for every component, for each joint, and for every feature of the circuit board. And so consequentially we're not looking for higher temperatures than necessary for the smaller devices in order to ensure that the larger devices do reach a point above liquidus which is adequate. But the other thing to note from this is simply because we don't have the need for this plateau period in the profile, our actual overall process cycle time is significantly less than it would be with convection, and consequently our thermal saturation is reduced, leading to far better yields, far better in-field reliability. This is a profile taken from a typical circuit board, and you can see the effect of convergence here. In essence, we've taken a low mass device and a heavier device, and whilst the low mass device does ramp faster than the high mass device, they do both come together and they converge at that peak temperature. So you've got 0 delta T's and ramp rates which in this profile are in the order of 1.1 degrees C-Celsius, which is well within inside the process parameter norms, and also recognize that this preheat was conducted in the vapor. This was not preheated in convection or preheated in an IR station and then transferred into the vapor phase system. This whole process from start to finish was conducted in the vapor phase machine and consequentially was oxygen free. That's it for that section. Next session we will cover oxygen free benefits and the use of the PFPE fluids.